Another night at the museum. I am Professor Toby Ault. I'm a climate scientist at Cornell University. And this is not the only Neil Young reference I will make, either directly or indirectly, in the course of this class. But tonight's lecture is called Heart of Coal, and it's the first one where we start to make a really direct connection between geology or geologic timescales and paleoclimate, paleo-environmental changes, evolution of life, to our current energy system, which relies so heavily on fossil fuels. This is a picture of a model of a coal mine, not an actual coal mine, that I took at the Technical Museum in Stockholm, Sweden. And right here, if you walk downstairs and a few rooms around the corner, you will find some examples of the rocks that give the Carboniferous its name, which are these carbon-rich, carbon-containing rocks we call coal. In this case, anthracite, which is a very pure form of coal. It's almost all carbon. And I think it's quite beautiful to look at. It also happens to be flammable, and it has a very high energy density, which, if you compare it to wood, is advantageous. It was advantageous in many parts of the world, Western Europe in particular. If you could harvest coal, you could burn it to make heat, and this was done for hundreds of years. We're going to talk about this period called the Carboniferous. I want to put everything onto our geologic clock. So we're imagining compressing the entire Earth's history down to just a 24-hour period. So we're imagining that right now is the final second of the day, and that the crust solidified at 12 o'clock this morning. This period of the Carboniferous occurs after the Cambrian explosion, which on this geologic clock, even though it was 500 millions of years ago, more than 500 million years ago, would have been equivalent to having it happen at 9:07, which is very close to the time that it really is. So we're almost, on today, we're almost getting to the Cambrian. We're actually going to talk about the Carboniferous, which, again, in this compressed time scale, this relativistic time scale, would have been from 10:05 p.m. through about 10:24 p.m. One of the other hallmarks of the Carboniferous is the presence of giant insects, giant by our standards. I'm sure the insects at the time thought they were perfectly normally sized. There's an example of a dragonfly that had about a 2-foot wingspan right here in the museum that I hope you'll find in the Carboniferous room. There are also centipedes that were almost, centipede-like insects that were almost 2 meters in length. And this was made possible by much higher oxygen levels during this Carboniferous period. Right now, oxygen is only about 20% of the atmosphere. During the Carboniferous, it was closer to 38%. It's almost double what it is now. Insects don't have lungs like us. We can move air in and out of our lungs, which means we can exchange oxygen and CO2 more quickly with our environment. Insects don't have that. They require diffusion to get oxygen into their interior parts. So having higher oxygen during the Carboniferous period just meant that they could grow to much more massive scales and still get enough oxygen into their insides to support their lives. I mentioned this briefly, but go over it again. Anthracite, it's a form of coal. It's a high carbon content, which means it has a very high energy density. Energy density is one of these foundational concepts that we're going to keep coming back to throughout the climate and energy lectures. What it means is that per unit of mass or per unit of volume, let's think about it as per kilogram, how many joules can you get out? How many units of energy can you get out to do work? Carbon, because it's a very high carbon content, very high energy density, all that carbon can easily combine with oxygen in the air and can be used to heat homes or to do work. It's formed from ancient plants. So now we'll just do a little thought experiment. Where did that carbon come from? Carbon that was trapped in fossil fuels, trapped in coal. Where was it? Well, once upon a time, it was part of a plant. Okay. Well, before it was part of a plant, where was it? Oh, it was in the atmosphere. So plants did photosynthesis, pulled the CO2 out of the atmosphere. Geologic processes buried the plant material beneath the surface of the Earth. Over time, with immense pressure, it was converted into the hydrocarbon resources that we're using today. And by burning those fossil fuels, it's sort of like we're taking those ancient atmospheres that were trapped in plants and then trapped in the Carboniferous and releasing them back into our own present day atmosphere. And we reflect on the life forms that existed in these very different climates, some of them much warmer climates. It might give us pause to think about what kind of climate we might end up with if we continue down this path. How did we get onto this path in the first place? How did the Industrial Revolution get going? A lot of it has to do with coal and its high energy density, and a particular fact of history that the UK happened to have a number of near-surface coal deposits that were used for several centuries before the Industrial Revolution just for heating. And because they were near the surface, they could be harvested or mined relatively easily. But because England's a very wet place, it wasn't as easy to get deeper down into those mines. Before we go deeper into the mines, I'm going to introduce or remind you of the law of superposition, which is one of these really foundational but intuitive concepts from geology. And it simply states that within a given sequence, an undisturbed sequence of layers of rock, the older stuff is going to be on the bottom, the newer stuff is going to be on the top. Just like if you're making a layer cake, you make the first layer, put it down, okay, that's the oldest one. Now you go back to the oven, you get the next one, you let it cool, you put it on top, get the next one, 3 layers, 4 layers, however many layers you're making on your layer cake, the oldest one is going to be at the bottom. Just that's the way that the sediments would be normally deposited. Other processes can change that. They can cause it to deform, they can cause it to be eroded away or overturned. There's lots of other processes that are important, but initially this law of superposition is going to be useful for us to understand our coal deposits. So once upon a time, a long time ago, there were no trees on land with woody tissue. There were other types of plants, you can learn all about them in some of the exhibits downstairs here, but there's no woody tissue. The first phase of plants moving on to land. Woody tissue was an innovation that wouldn't come along for a few tens of millions of years later. And it required this tough, long, very high integrity molecule called lignin to comprise cellulose in the structure of the woody tissue of trees. And that's what would allow them to grow to impressive heights, the impressive heights that we see now. But when they first evolved, there weren't bacteria that could readily break down the woody tissue, this lignin molecule, which is a long, tough molecule. It had evolved fast. It was like an arms race, and it outpaced any microorganisms that we have now that can digest lignin. Like the microorganisms that you find in the guts of termites didn't exist as far as we know. And because they didn't exist, you have to think of wood in the Carboniferous, the early Carboniferous, almost like plastic in the environment today. Or bone, maybe, where it just accumulated and accumulated and accumulated. Now, a lot of it burned. There's evidence of mega fires during the Carboniferous, which checks out because you had high oxygen levels and lots of potential fuel sitting around. But not all of it burned, not all of it back into the atmosphere. And it was this imbalance of more CO2 going into the plants and getting stored in the terrestrial system that caused not only CO2 levels to go down over time in the Carboniferous, but also oxygen levels to reach that really high level of 38%. So through time, trees grew, they died, their woody parts accumulated in bogs, accumulated on land, accumulated on top of each other, piled up like ruins in Rome. If you've ever been to like a European city where the city surface that you see is built on the ruins of older cities, which are built on the ruins of older cities, which are built on the ruins of older cities. It's kind of what was happening over millions of years of time scale, millions of years. Sediments deposited on the surface, and eventually a new environment comes through, puts on new layers of sediment, and as more and more sediment accumulates above this layer that's rich in carbon, full of bits of plants that never rotted away, heat and pressure and time is going to convert all that organic material into coal. And then with plate tectonics other forces that act on this layer, these layers, layer cake, the stratigraphic layers in our example here, could have caused it to deform, so you get ripples, or think of them like waves. Almost like if you had a soft candy that had different layers in it, you press it from the side, you might get these ripples. It's analogous to what I'm trying to show here. And then you get erosion on the surface, stripping away the top layers. And in England, this happened to the extent where you could find these ancient deposits of carbon that we call coal. And look at them, they're so happy, these English coal miners. They found coal that they can mine. I guess these are probably the mine owners, that they're the ones that are happy because they found coal right near the surface. And they're going to be able to initially harvest or mine away the coal near the surface, but they're going to encounter the water table. And as you get deeper and deeper into the mines, the water pressure increases as a function of the depth. So you have more, as you have more depth of water, you have greater force acting on the water table from the sides and pushing water into the mines, which means that they had to have some way of removing that water efficiently. And they had pumps. They used pumps that were driven by either humans or animals. They had horses or mules that would walk around in circles and buckets up out of the wells, out of the mines. But they just weren't very efficient. They couldn't keep up with the water that was always flowing in from this very shallow water table until the invention. There were several other attempts before James Watt's steam engine, but the invention of the James Watt style steam engine was efficient enough that you could use coal to make steam, to drive pumps, to remove water, to mine more coal, and you could do a lot of other things with a steam engine as well. Because once you had this way of converting a very high energy density resource like coal into thermal energy, into kinetic energy to do work, not only could you dig deeper, you could have steam engines on trains that took the coal to other parts of England or other parts of Europe. You could have steam engines on ships that could go all around the world. Coal is a relatively stable hydrocarbon compared to like what we use now, natural gas or oil. It's just not as volatile. Of course it can light on fire, but it's not going to explode as readily as some of the hydrocarbons that we use today. So you could load up big steamships with coal and have this high energy density resource almost anywhere in the world within months of mining. And this, I cannot overstate how absolutely transformative this was in human history. It's analogous to the Cambrian explosion of life, which you can learn all about downstairs in the museum tonight. It changes everything, because for thousands and thousands, for 50,000, 100,000 years of human history, the energy that humans had available to them was either food that they ate, animals that they could work with, work animals, horses that they could ride, which maybe didn't compete with them for the same food resources. Horses eat different food from humans. So you could use the work of a horse, the work of a mule. Humans had to eat food to do the work. Or there was biomass that you could burn to make heat, but that biomass had to grow on decadal timescales, decadal timescales. So the wood that was available for smelting or other industrial processes or pre-industrial processes had to have grown on trees that existed or coexisted with the humans that were using that energy. So for centuries and centuries, millennia upon millennia, the energy that humans had to use at their disposal was very limited fundamentally by how slowly trees and vegetation grew, either to make food for animals, food for humans, or to make fuel in the form of wood. Coal changes absolutely everything because now humans have access to a very high energy density resource that is flexible enough that you can do things that were unimaginable to just a generation or two earlier. And we're still living out the implications of that. We still have a fossil fuel-based economy, and every few generations the world looks totally different from the way that it did a few generations back. Every 20 or 30 years the world becomes revolutionized again, and it's analogous to this Cambrian explosion of life forms. The technologies that you have at your fingertips now weren't available 20 or 30 years ago, and they all depend on very high energy density resources, hydrocarbons, that are relatively low cost in the current global economy. So now we have a situation where Still today, and starting in the Industrial Revolution, you can dig arbitrarily deep and just pump the water out of these mines and dig deeper and harvest coal. Quick redux. Coal was used as an alternative fuel for heating even before the Industrial Revolution. But it wasn't until really the invention of the steam engine and all the other industrial processes that made possible that we started to see it becoming such an important fuel type. We'll get into other fossil fuels later in the course of the semester. And there are more ramifications to this change than can even be enumerated. I think a person could spend their entire life listing the ways that the Industrial Revolution has changed the human experience and run out of time, even if you live to be 125, because every new day there are a trillion new uses that are possible for this low-cost energy source that we first started relying on in the form of coal, and then we switched over. We're still using a lot of coal, but we've also become very reliant on natural gas and oil, which is also a fossil fuel that we'll talk about in lecture 6, so pretty soon here. We'll stop there. Take your chair. Take it with you. Actually, we can stack them up on, we have a cart for the chairs. So we'll stack them up on the chair cart. And we'll meet you in front of the Velociraptor. So go find the Velociraptor, and that's where we'll reconvene in about 10, 15 minutes. It'll take us a little bit of time to get the next round of video cameras set up.